So the beginning of this notebook, a lot you can skip over. There's a lot of redundancy with what you've seen before. When you make your code, fill in between the two signal comments. And then there's this debug variable. Just when you execute the notebook, make sure you execute one cell at a time. Or if you start in the middle, make sure you do a cell run all before. So run all above. So that's really nothing new. Here he just warns against naming variables with all caps. So now this auto mark is not true. I'm not using it, so don't worry about that. So all this stuff up here, don't waste time reading it. You don't need to read all this junk. You can set the student number, might as well set that, and you can do this debug. Just run it pro forma. All right. So reading in the data, you will need this file planar utils, which is also in the Google Drive. This planar utils generates simulated data, so you're not downloading any data, and you don't have any data file. It's kind of the data is kind of interesting, but you'll get a chance to see what the data looks like. Actually, maybe I can just do this and do run all above. Let me take a minute. Okay, well that was fast. Okay, I'll run this one too. Okay, all right. So for instance, here he gives you a picture of this noisy moons data set. This is the data. Now this is typical classification data. You can see two features and then the class here. So this is binary, a 0, 1. And then here he shows you the data. So it's called noisy moons. If you look at the data, you can kind of see why it's called noisy moons. Okay. So you're going to ask your neural network to distinguish between these two classes. And there are some data sets that are not binary. If I go back and do blobs, for instance, I think blobs is multi-class. Go back up here, and I do this. Let's look at blobs. Okay. And run. So there's the blobs data set. All right. So if we go down, so I think we start out with noisy moons. So set it up with noisy moons at first. Dividing the, so this should be familiar stuff, training and testing set. This uses the automatic Python routines. Here what he does is he divides the data in half, training and testing, but then he divides the testing set in half, and one half is for cross-validation. So what you do with the neural network is you train it, and then you validate, and then you train, validate, train, validate, train, validate, until it stops improving. So you'll see how that works out. Okay, so then here you can, I think you've seen this before, you scale the data. Did I execute this one? I did not. Okay. All right, so far there's really no code that you had to write. Okay, so he scales the data for you. Okay, now, one hot encoding. That's something that you may or may not have seen, but that is in the slides. The idea is that, well, I can just do a quick example. I think I do have a quick example of it. Let's find it. I think it's the last one. Let's zoom in and see what we have. I think it's up here. All right, yes, it's here. Right. So for instance, if you have binary encoding, like this is kind of a rough picture of the data set. Here you got your two features, x1 and x2, and here's your class, y. Now here you'd have several rows of data. The person's in. Okay, you have several rows of data. Okay, and here's the class here. Now, if the class is, if you actually have three classes in the data set, it will show up as 0, 1, and 2. So this is the classification. But when you're doing a neural network is not good at doing that. So what you do instead is you translate the 0, 1, and 2 into a vector. So your output will have three nodes. So 0 means you put a 1 in the 0th place of the vector. A 1 means you put a 1 in the 1's place. And a 2 means you put a 1 in the 2's place. Remember, Python, the first place is the 0th place, 1th place, 2th place. Right? So this is called y, and this is called y hat. So it's kind of a transformed version of y. So the rule is, if y is 0, y hat of 0 is 1. If y is 1, then y hat of 1 is 1. If y is 2, then y hat of 2 is 1. So from this rule, you should be able to implement one-hot encoding. Now in this case, you will need a loop. I don't know of any way to do this without a loop. But it should be fairly straightforward. A loop with basically one line. And that's in the code down here. Right? So this y hat is what you'll create. So this one-hot function will return this y hat, and he returns it as type integer because you do want the output to be zeros and ones. Actually, I don't know if that's such a good idea to return it as an integer, but I guess it works, so we can do that. So this is where you would create it. Now you have to think about what the dimensions of y hat is. Here you put y hat as NP array of 0, but that's really when you dimension y hat, you should figure out what the dimensions are. What's the number of rows of y hat going to be, and what's the number of columns? And then you should dimension y as an array, y hat as an array, and then fill in the 1 entries. I think that's the easiest way. Initialize y hat as an array of zeros of the correct size, and then put 1s in where you need to. Right. And then here he gives you some examples. So you should try out your code with these. Don't just try out your code with two classes, because it has to work for two classes or more than two classes. Right? So those are some examples you can do. All right. So I will say that what we're doing in this notebook is not something you would do in practice. It's kind of showing you how neural networks work, but all this stuff is done for you automatically in Python. It's kind of like when you did logistic regression, linear regression. We went through all the steps, but then at the very end, you saw that there's a Python function that did everything. Okay, so what he does is he uses a dictionary. And you know all about dictionaries, so that's good. So this dictionary is used to contain the weights of the matrices at different levels. So just to remind you, for a neural network, I think I can look at this one. So you will probably have to refer to the presentation when you're doing these codes. Let's see if we can. Here we go. All right. So if you remember neural network structure, you've got layers. and you've got connections between layers, and the connections between each pair of layers corresponds to a matrix. And the size of the matrix is related to the number of nodes in the consecutive layers. All right. So to specify the neural network, you need to specify what these weights are. Now notice there's the one node which is a little bit different from the others, and I've been calling these weights the biases, the ones that have subscript 0. But you can think of them all as weights. And if you do go through the presentation and watch the videos, you'll see how this works to create an output. There's a systematic procedure, and that's called forward propagation. So, excuse me. Okay, so, all right. So these are functions. Apparently, he has some pretty fancy display that shows the matrix sizes and summary of the matrices. And so, for instance, here's an example of neural network weights. So theta 1 would be the weights that are joining the first layer and the second layer. The theta 2 would be the weights joining the second layer and the third layer. So the superscript is always the index of the layer you're coming from. Right? So here, if you look at how he set this up, so this is pretty nice the way this works. He's using display, and the examples that he prints here, if you go back here, you will see, where did he set his thetas? Wait, this is a big code. He defined theta somewhere. I guess it's at the bottom, because he called the function. The function is defined first. All right, so yeah, so here he gives a particular example. So you can see that this is a dictionary. The first key is 1, and the second key is 2. And then we have 2 arrays here. And then when he calls the function, here he's printing. Print MD is a formatted print. He's printing the theta 1. Then here's printing, here he shows a different way of printing theta 1. You don't just show the entire theta 1, you show the first 3 columns and the last 5 columns. All right, so you can see how this works down here. Right. This is the result of the first print, printing theta 1. I'm sorry, I guess the key is not, well, no, that's right, okay, that's fine. And this is the label. This identifies the matrix, and then this is the label. And then here he does the second one, where you can see he shows the first 3 columns and then the last 5 columns. And then here, display the first and last column. That would just be here, and he puts the dots between. So if you read this code and you compare with the outputs down here, you can see what the code is doing. Now you can show some of the columns, you can show some of the rows. So that's a nice function if you want to print out your matrices. All right, so first of all, you need to initialize. Usually when you have a code, you need to initialize your variables. So you're going to have to create this dictionary. Now you create the weights at first, and then the weights will be adjusted during the process of training. But you have to get the size of the weights right. So he discusses that here. So here he says, when you create the weights, you want to use this function, np.random.rand. Okay. So you'll start with random weights, and then the algorithm will train them. And here he talks about what the sizes will be. So you can read that. You need to make sure that the dimensions of your thetas are correct. Now, one thing that's confusing is that, which was not a very good choice, is he uses L as a variable. So be careful if it's an L or a 1. Okay. This here is an L. This here is an L, not a 1. Right? Because this is associated with layer L. Right? So layer L has a set of thetas, and the size of the thetas L matrix is here. So make sure you don't confuse the L and the 1. Okay, this is also an L here. Now when you do generate the weights randomly, you use this random seed, which makes it so that it generates the same random numbers each time. So if you leave this the same, then the random numbers that you get will be the same as the random numbers he did. However, there's a caveat. All right, so here says get your random thetas array. So this code is for initializing the thetas. So what this does is it steps through the layers. He starts with layer 1. I guess he doesn't use the 0. And then here, these are the sizes, N1 and L. That's NL, not N1. And then L plus 1. So when he zips, he puts these arrays together. And you can see why he does it this way. Here he's going through the layers from 1 to the length of NS. NS is the number of layers. So actually it's going from 1 to the number of layers minus 1. Of course, because there are no weights that go out of the last layer, only weights that go out of the last layer minus 1. Then NS goes up to minus 1. These are the layers, all the layers except for the last one. And then here are the layers that don't except for the first one. Because when you connect two successive layers, the first connection is going to be between the first layer and the second layer. So you're going to start with the first layer, but you don't, like I said, you don't connect the last layer to anything. So when you do your connections, you end with the last layer minus 1. Okay. People still there? Just want to make sure. Just want to make sure. Okay, good. Okay. Because if you get cut out, then I don't know. All right. So if we do get cut out, just wait a couple minutes. I can get back on. I'm very thankful about the connection today. All right. So, so if you did this right, he gives you some things to check. And he tells you if you set your layers, it should look like. Now, I had people do this, and they didn't get quite the same. No, all right, here they did get the same results. So it wasn't here that was the problem. And, okay, so here he does thetas to try. Here's where you test the code. Now, when you test the code, you should put in different numbers here and get out the different results that are shown up here. All right, so make sure you do some thorough testing, because in this one, if you get one step wrong, then everything goes wacko afterwards. So make sure that you get all the steps working before you go on to the next step. So sigmoid function, that's going to be our activation function for each neural network node. And you've done this before, so you can go back and copy your code, or you can just write it again. That's the same function for logistic regression. So that's the activation function that will be, remember how this works if you've watched the video, that when you do a neural network, for all of these nodes will influence the value here. And then once you do the linear combination, then you apply the activation function. So we're applying the activation function for every one of these nodes. Right? So it's important you get the activation function right. Then you do forward propagation. Forward propagation is how you get the neural network output from the inputs. So again, if you watch the video, you have the notion that when you go from one layer to another, this represents linear combination, and that creates a z. And then to get a hat, you apply the activation function to the z. Now z and a hat are vectors, but if you write your activation function correctly, the activation function will act on all the components of the vector, and this will be correct. Then to get the next layer, you can read this, but to get the next layer, you have to modify a hat and add a 1 at the beginning. Right? And that reflects the fact that when you go from one layer to the other, these nodes generate these two nodes, but not this one. So you have to add this node when you get to the next layer. So when you propagate forward, you create a hat for the next layer, and then you add 1 at the beginning. There is a function called insert that you can use for this. So in his dictionary, he created spaces for z, a hat, and a. And you will write code that generates these layer by layer. Indeed, just go back to the description. It's pretty thorough. All right. So here you can see he's setting out empty dictionaries. And what you do first is you do the first one outside the loop, and then you create a loop that does the subsequent layers one by one. Now, when you have this, you'll erase these brackets. You don't put your answer inside the brackets. That's just a placeholder to show that something goes in here. Right? But don't put your answer inside the brackets. Okay, so you're just going to, for a hat and a, you're just going to implement the formulas up here. You'll implement the formulas up here. You'll create z, a hat, and an a. So I think the loop is pretty simple. I think there's just those 3 statements inside the loop. Okay, let's see. And here he gives you something to test. So you should make sure that if you put these thetas in, then you get this kind of output. And he tells you exactly what you'll get. So I think he gives several examples. So make sure those check out. Okay, then we got the cost function here. So description of the cost function. So that's just at the last node, because what you're trying to do is minimize the cost function. The cost function reflects how well your neural network is classifying. So this is similar to the logistic regression cost function. Should be able to get that done. Now this is where you may get some different answers. I had somebody do this, and they got, now your answers should be more or less the same. I think that the person that I checked this with, in this output, he didn't get 8.72, he got 0.83. But it should follow the same pattern. Like when you do your outputs, it should be roughly this size. The output that you get here should be roughly this size. But if you don't get exactly these numbers, don't freak out. You're probably still okay. But double check your cost function just to make sure. Well, that's probably going to be enough to do the first week, but well, I might as well keep going through. I still have another half hour. Are we still there?
Yes.
Okay.
Yes, we're here.
Yes. Okay. Good. Okay. So here, once you get the output, of course, you make predictions. So you make predictions like you did with logistic regression. Now, in this neural network, there are two cases. When you're using two classes, you have a single output node, and you're just using the same criterion for determining the classes with h theta. Now, of course, h theta of x is greater than or equal to 0.5 is the same thing as saying that x is greater than or equal to 0. So you could do it that way. But if there are more than two classes, you have to do this. You have to do it the other way. So if the number of classes is greater than 2, look at the output node with the highest value. So, like he said, you should be able to do this just with indexing without using a loop. Avoid loops whenever possible. Okay, and again, some examples that you should check out with. All right, now here's the really complicated thing. Backpropagation. Now, backpropagation is covered in the 4-2, and that's here. Now, I did make a video that goes over the math, but I have not yet made a video that goes through the steps of backpropagation, the way he implements it. And let me just give an indication. So when you're implementing backpropagation, you're probably going to have to refer directly back to the slides. And he does a detailed worked example for how to do backpropagation. So compare your steps with the steps that he has here. So it's probably worth my talking about this. All right, so here's an overall description of backpropagation. You're going to step backward through the layers. So you will have a loop that goes backward through the layers. So briefly, if you start out with this data set, all right, here you have 2 rows of data, and the rows of data become columns in the input matrices. And notice he added the ones, okay, to reflect the. I'm going to do that. Go back. Okay, so he added the ones to reflect the one node that's added here. And then he set up the thetas. The thetas here reflect the thetas in this picture. All right, so here you're setting it up. Why don't I do the slideshow? How about that? From here. Right. Then go down. Okay. All right, so these are the classes for the two. You had 2 data instances, and these are the 2 results. So you start with your Y. So you convert Y to one-hot encoding, so there are 2 unique labels. Okay. All right, so here he's doing the case. He's doing the case where you have 2 nodes. You might have 1 node, or you might have more than 2 nodes, but the procedure is similar. Right? So here he's converting the Y to the desired output. So here's your Y matrix that gives you the output that you're going to compare your input to. So then you do forward propagation, 1 step at a time. So you'll generate A from your X's, then you generate, no, all right, A1 is from the first layer, which we have already. Then A hat 2, because there are 3 nodes here, you get a 3 by 2 matrix. and because there are two data instances. And then for A2, you add 1 to the beginning. All right, so this is forward propagation, which steps through systematically. So I think you can follow this. All right. Now you don't add 1s at the last layer. All right, now here's where you follow the steps that he gives you. And you compute your delta is your prediction minus your actual. So you just compute that. That can just be you don't need any loops for that. You just do a straight negative. And that's the delta for the last layer. And then you have to compute deltas for all of the layers, because you have to compute derivatives with respect to all of the weights. And so you go down from from L minus 1 to 2. So for each delta L, discard the first row. So why do you discard the first row? Because the back propagation is kind of the reverse of forward propagation. In forward propagation, you added the first row at each step. So now you're going to discard the first row. So here we have, so in this case, because we have 4 layers, the first one we're going to compute is delta 3. Here is the weights for the last pair of layers, transpose, multiplied by delta 4, which you already computed. And then this is element by element multiplication. And then you multiply it by this mysterious factor. Now these are vectors, but you can do element by element operation here. Are we still there?
Still here.
Okay, still there? Okay, good. Okay, just checking in periodically. This actually turns out to be the derivative of the activation function. He doesn't explain that, but that's why it's there. So if you go through the math example, which I can show up briefly, is it here? No, that's not it. Yeah, it's here. So in the mathematical expression, when you're doing back propagation, the derivative of the activation function, phi prime, appears in the expression. So this term here is the derivative. Right. So we go through. So delta 4, so you'll carry out this step in your loop. So you get, so you have all the components here, so you get your delta 3 and you multiply them together and you get delta 3. Then you discard the first row, which is a good thing because it's all zeros anyway, and you get delta 3. And then to get delta 2, you carry back from delta 3 the same way you got delta 3 from delta 4. Right? So delta 2 has this same formula, except we replace delta 4 with delta 3, and delta 3 with delta 2, and A3 with A2. Right. So you have all the components, you put it together, and then you discard the first row. Okay. So you're going to get all of these deltas, and then you use this formula to get the partial derivatives. Now, this also was a little bit confusing. When he says d theta L is the same thing as what he calls d theta. Okay, where's my slideshow? It's here. Okay. I think it's back here. Well, here, let me go back to the slide so I can see where it is. If I can find the formula. I think it's here. Yeah, here. dj d theta. This is what he's calling d theta j, because that's the change that you apply to theta j. So this expression here, dj d theta sub j, is the same thing as this, what he's calling No, where did I put it? Oh, I screwed up, didn't I? Let me go back. That's the same thing as d theta j. It's the same thing. All right. So let me go back to my slideshow from here, and from current slide, and go down. Okay. Go down, do all this stuff. So bottom line is, do refer back to this slides to get the steps correctly. And they're very clearly set out, and it's just a very nice and complete example. Okay. And that's going to be the hard part, I think, of the programming. All right. So you'll put that in here. All right, and then here he gives you some things to check against. Okay, and some more things to check against. And then your old friend gradient descent. All right, and he actually implements that for you. Okay. All right. Let's see. Well, I think I will stop here. Because we can talk about this next time. I'm sure that's probably enough for a week to get all of the theory down and understand what's going on and to do the programming. So I think we'll stop here, and we can talk about this one next time. But this does bring together a lot of stuff that you learned before. Okay, one last time. Are you all there?
Yeah, we're here.
Okay. All right, wonderful. Yeah, wonderful. Okay. All right, so that's my spiel for today. Do you have any questions? And I think I did record. Wonderful, I did record, so everything should be fine. And I'll post this in the usual place. I'll send you a link by mail. And I'll also put the link in the Canvas assignment so that you have it there.